Thank you for watching Idealized Science Institute's long-form videos. Here, our goal is to help teachers teach purposefully. We have deliberately slowed down the process so teachers can dissect the lessons and find those hooks that will engage their students in authentic scientific practices. Now, these lessons are sequential, so please watch them in order. And if you like what we're doing, consider supporting the Idealized Science Institute. Visit our website where you could see other long-form videos, our podcast, we have quick quizzes, and so on. And as always, please put comments down below. And we are really hoping to hear from you as you enact some of these lessons in your classrooms. So we're back in the shop, and we're trying to figure out how to measure the size of this ball, the diameter. There's a whole bunch of different ways, and students might come up with interesting ways, and you want to encourage that. And just like a mechanic, we need to know the size of this sphere. Often they'll be using ball bearings. This is a piece of wood. The first way that students might try to do this is they might simply just try to take a ruler and put it next to it. Maybe they could kind of get it level here, something like this, and say that's like about 1.2, 1.3. That's a difficult one. There's other techniques that we can use. We can use a Vernier caliper. Now, these Vernier calipers work really well, and it's worth learning how to use these. We could take this, put the ball in between the jaws, pull it out, and then we can simply read off here. Now, a mechanic can't use something like this when they're talking about a ball bearing. Just like engineers want precision, a mechanic needs to know things down to as many sig figs as they can. So they might end up using a dowel caliper. Now, this dowel caliper, it's going to be a little bit more difficult to learn how to use. There's gradients on both sides, and then you have to use the gradient on the spindle. But if I put this through here, I can see, oh, it fits right through there, but other times it doesn't fit through. Let me see if I can show it on a different angle. It goes through this way, through that way, but if I try to rotate it in here, it gets jammed. In other words, this ball is not round. Its eccentricity is too great on one side compared to the other. So in other words, this is not a perfect sphere. And you could see how it rolls. So this is going to be a problem for our system. In fact, now that I can detect using my measuring device that it's not round, I can actually see that it's oblong. To a great degree, it's actually more egg-shaped. So we're probably not going to end up using this. But the techniques that students can use to measure a sphere, here's one that is also fascinating. Sometimes you have students that work in a shop and that have an engineering mind, but maybe they're a mechanic. They'll say, why not just use sockets? So these are measured in millimeters. This is a 12 millimeter socket. If I were to try to put the sphere in here, it doesn't fit. If I were to put it into a 13, it drops right down. So right away we would know that this ball is somewhere between our 12 millimeters and our 13 millimeters, using whatever tools that you can. So this is the most crude, gives us a ballpark. Using our rulers and trying to manipulate them and try to figure out where the top and the bottom of the ball is, assuming they're parallel, is maybe a little bit better. Caliper Vernier caliper would be really great, and using this dowel indicator would even be better. Whatever tools you have available, that's what you're going to use. Whatever tool that you're using, take the time to help students understand these. It's going to help them in future projects and possibly their occupation. All right. Now we're back. We realized that we're not going to drop the wooden ball. The wooden ball, its eccentricity is too large. It's kind of round, but not very round. Students will say, let's use a ball bearing. And a ball bearing is going to be nearly perfectly round. They're absolutely precision pieces of metal. Let me show you how to get the exact value on this. And I have a Vernier caliper. Let me see if I can put this onto the computer. I have to set this down. I have to change my glasses because I can't see using my typical ones. So put these on. All right, so now I've got this ball. Notice I'll put it right in the jaw, just to where it ends up being able to go through. You'll notice at the top it says the fraction. That 0 is what we're going to read off of. But really, we need it down into millimeters. That's what we're going to end up using. So I can either convert half, because it looks like exactly half, but we might as well learn how to use this. You'll notice the 0 on the bottom jaw is past, looks like 10, past 11, past 12, and it almost looks like it's getting to the, it's not quite at the 13 there, so it's going to be 12. Now I use this bottom part right here, and I find which one of those lines lines up perfectly. Make sure the ball is not moving through here. One of the tricks that I do is I'll put this through, and then I will squeeze so this does not move. Now I can say that's 12 point, looks like the 5 lines up on, actually I'm looking at the camera here. It helps me magnify this to see which one of those lines lines up. Looks like our 8 lines up perfectly. Okay, so we would say 12.8 millimeters is what we would end up using for this ball. That's what we think it is. So we can put that in. We're going to have to convert into, let me put my other glasses down, the metric system, but I go right back down here, and this is where I'm going to end up putting my number of meters. So I convert that as point. There's a flaw with this program. I don't know why, but you have to hit the decimal point more than once. 0.0128, I think, is what we said. Okay, so that's about a little bit more than a centimeter, and then I'll hit done. Now when I drop this through, I should be getting really accurate values. Let's try this out. I'm going to hit collect, drop it through. And I got 3 values. It looks like one of them is going to end up being a bounce. So I have a 5.4 up here and a 1.26. Let me make sure that I have my photo gates. This is photo gate 2, and it looks like I have it connected to digital slot 1. I have the photo gates reversed. Now, I did this. You imagine your students are going to do this also. It's up to you to decide if you're going to tell them this or if you're going to let them figure this out themselves. So it seems odd that we would have a faster speed after, or to start with. We should have our slower speed. It should be picking up speed. Now that I know this, I'm going to switch this out. I could use those values, quite honestly. It's not a problem. But I want to switch them. I want it to look the other way. Oh, and I never hit stop, so let me hit stop. Now, I will say, whenever you do this, often it is best if you get out of the system and come back in. You're just going to have less problems. So I'm going to go back to my Vernier. And there's nothing wrong with doing this several times because it doesn't take long. Plus, you want students to be able to think about, oh, this system is available if I want to measure other things. I'll go up to Vernier. I'll maximize it. I'll go to my speed through gate. I'm going to use a flag option. And I'm going to put my 0.0128, I think is what we measured. And I'll hit done, and now I can drop this again, and I'll hit collect. See if this works. Go around my table. In this case, I get velocity 1, but not velocity 2. So, how can that be? And it got 3 of these. So there's all kinds of issues that are going to arise here. First of all, this wobbles. I might have ended up, dropping this at one edge or the other. So one of the things that you can do is you can just use a pen or something like this. We're going to recollect. I have a pen here. Let me hit collect. Actually, it never stopped, so I'll hit stop, and then I'll collect again. I should have 2 photo gates working here. So I'm going to end up hitting collect. And what I'll do is I'll run my pen. Oh, I can see right away my problem is, again, it got out of line. And my photo gate up top there is red. And I need to fix that. Part of it is my apparatus is just wobbling too much. Now, you can tell the students, try to fix this now, or they can suffer through it. At some point, they're going to end up saying, it's not worth it. I really just need to fix this. There we go. See, I bumped the apparatus and it knocked it out of alignment. So I'm going to try this again and come over and hit collect. One of the things that I can do is, just for a practice run, is I can just use my pen and I can put it through the beam just to make sure that it's working. And you could see that I get my 2 dots here, my first velocity and second velocity. And I'll hit stop. Sometimes you don't want the graph, you just want the data table. I'll take the graph off. I already looked at data set 1. I don't want it. I'm going to delete that one. And here's my second one. Here's my first velocity. Here's my second velocity. Now, we just switched the photo gates, but sometimes these read backwards. I've been working with Vernier for now 25 years, and sometimes it just reads backwards. It just does. You can't stress. You got to understand that it's worth using them even if there's a glitch with your computer or whatever it is. Let me drop this back down through. I'm going to have data set 3 now, so I'm going to hit collect again, and I'm going to drop it through. And I get velocity 1, but I didn't get velocity 2. Now you might be thinking, wait a second. I thought we fixed the Vernier system. And students can drop over and over, and sometimes they'll find the first photo gate doesn't seem to be working, and the second photo gate doesn't seem to be working. At some point, they're going to realize sometimes the ball is missing the beam, plain and simple. Now, should you tell them that? That's up to you. I would give them time, and it depends on how much time you have to dedicate to this experiment in your class. You can't do this for every experiment, but if you can get 1 or 2 of these where you really extend the period of time, let the students problem solve. What's happening is the ball is simply too small that it can end up passing through here. The little beam on our photo gate is very thin. It might miss it altogether. So if you tell them this, or they come up with their own idea, they might say, hey, do you have a larger bearing? And I'll say, you know what? I have this bearing. And this bearing, it barely fits in this tube. I can feel that there is almost no play. In fact, it's almost a tight seal. They're going to say, we should use this one. Problem is, you heard that I didn't have anything to stop that bounce. Very loud, probably dented the sphere a little bit. So what I'll do is I might say to them, look, we do not want our bearing being dented. We need it to be a perfect sphere. So they might put a magazine down. You might recommend getting some paper towel or something like that that is going to help slow that down so it doesn't crash in. So let's try now a larger sphere. Again, I'm going to need to end up putting my value in here. This is exactly a 1 inch. So we'll be able to put that in as our, we know the conversion is 2.54. So I'm going to get rid of this data here. I'm going to stop. I'm going to get rid of at least one of the data sets. Delete. I'm going to go back in, and I'm going to end up putting 0.0 or 0.0254. I know it's an inch. Let me get rid of my graph. I just want the data table, and I'm going to get a new one. So I hit collect. Hopefully this isn't going to be too loud. But you can hear that thing was scraping the side. And I got two velocities that are outrageously large. So I need to stop here, make sure that it did not change. Yep, my flag width, it got rid of those zeros. So look, don't fret. I can just put a 0 back in here, a 0.0. This happens all the time. And now it'll change my values for me. And I end up with two values. It did not change my velocities. It's saying it's going 37,000 meters per second. So there's another problem here. And so that's what we're going to have to go through. So, whoops. Let me stop right here and see if I can maximize this. We're going to drop the spheres back through again, and I have my two velocities. You'll see that 1.571, and then that actually says for velocity 2, it's just reading backwards, and then the other one is 3.576. Just too hard to see when I had it far away, so I wanted you to see those values. We're going to now calculate. We now have our values off the computer. It's time for us to calculate what we should have gotten, and then we can measure what the beam distance actually is. Remember, we were trying to figure out if we know the velocity here and the velocity here, we should be able to calculate using one of our kinematics equations, what is the distance between them? And that's what we're going to do now. First thing we should probably do is draw on our apparatus. In our apparatus, the important parts are we've got a beam going across here and here, a pipe, and then we have some kind of sphere dropping down there. So let's draw that out. So here I've got my tube. Looks something like this. Comes down here. And the important aspects are that we have beams going across here. So I have maybe one photogate beam going across up here. And then I have another photogate beam down some point later going across here. And this is going to allow me to get my velocity initial, and this is going to give me my velocity final. And the way that we did that is we have to enter into the computer what the object is, the distance that's blocking it. So in this case, we used a metal sphere that is nearly identical to the size of the PVC. If that is 1 inch PVC or 1 1/4, whatever it might happen to be, it is going to be very, very close. So I'll choose something that's very close indeed. So here I've got a sphere that I'm going to end up dropping here that barely fits in there. And that sphere is, unfortunately, I mean, I could hear it when it was going down. It was scraping the sides quite a bit. I'm going to take my velocities off the computer. We said it was going a velocity here of 1.57, it looks like 1, and that is meters per second. Down later, it turned out to be 3.576. 3.576 meters per second. And what we're interested in is trying to figure out what is this distance in between these two beams right here. I want to know if I can tell from those velocities what this distance is going to be. When I measure it, and I have to measure the important part. Now, students will have to decide where they want to measure. Do they want to measure from photo gate to photo gate? Or maybe the top of the photo gate to another top of the photo gate? These are conversations that you need to have with your students. But just challenge them to say, what is actually taking the measurement? We need to think about a photo gate. A photo gate is a plastic piece, but there's a beam going through there. It's the beam that we are really interested in. So if I were to take the middle of this beam to the top of that beam, and of course it's going to be hard for me to judge here, but let's just call it 0.66 meters. Call it 66 centimeters. Let's see what we actually calculate with these values. So this is essentially our problem, and we know that gravity, acceleration, is going to be in a downward direction. Call that acceleration due to gravity, 9.8 meters per second squared. We verified that before. And I think we're in good shape. So we can think, well, if I have VI and I have VF and I have A and I want to solve for D, let's see. Equation 1 has time in it. I could use equation number 1, but again, challenge your students. If I use equation 1 to solve for T, and by the way, there's a T on our computer here, but we're ignoring that. These are all used internally so the computer can put the calculation in there. Remember, it got the V because we put the length of the object here. So from right here, we tried our very best to get that length right there, from there to there, of the sphere. Also known as, we could say that's the same thing as putting the diameter in. I should be able to use one of these equations to do this straight without having to do a second equation. Problem with doing two equations versus one, I get some experimental error in there. I'm going to use a calculator, whatever you have, just like when we were down in the shop. If you don't have a shop and you don't have a vernier caliper, use your meter sticks if that's all you have. No matter what it is that you have, use it. Use it to the best of your ability, whatever kind of calculators you have. If you have a calculator that can handle graphics, things of that nature, use it. But if you don't, use what you have. Nothing else. Use the calculator on the computer if you need to. But don't let any of the things slow you down or stop you by saying, I don't have this. Well, see what else you do have, then try to use that. All right, I'm going to use equation 2 because I have VF, I have VI, 2, we know what 2 is, and A, and I can solve for D. So it's important whenever you're writing these out, make sure that you don't skip steps. So I'll write equation 2. VF squared equals VI squared plus 2A and D. I want to solve for D, so I'm going to rearrange and write my VF squared minus my VI squared equals my 2, my A, and my D. And again, I'm looking for the distance, so I want to try to get D alone. So I'll write VF squared minus my VI squared, divide both sides by our 2 and our A, and then I have D. And we've done problems like this over and over. But now we have these numbers. And these numbers, we want to try and keep as many decimal places as we can. Whenever we have experimental results, we don't want to round. And the Vernier system gives us 4 sig figs. We're going to use all of them. So our VF, as we found out right here, is going to end up being our 3.576, and that is meters all over seconds, minus my VI, which is 1.57 meters per second, all divided by our 2 times our negative 9.8 meters per second, and that's going to be squared. All that equals D. Now, there's a problem already. These are not going up, but yet the computer is going to say 1.57. Computers don't know if things are going up or down. They're simply blocking things. So I need to put that these are going in a downward direction, indicating they're negative. So if you'd like to put a negative there, as long as you have a vector there, but I need to put this here, and I need to put that there, and these are both squares. So I need to square that term, and I need to square that term. What's important here is to notice that negative does not go away. So in this case, we're going to end up needing our calculator. Let's use this one. And I'll square each of these. Now, a negative square is going to be a positive. So 3.576. And I'll square that. And that turns out to be 12.78. 12.787, so I'll write 8. I have a little bit of rounding there, but meters squared, seconds squared, minus, and that's a positive now. This negative 1.57, so 1.57, 1. I had one more decimal after that, right? Yep. So I can square that, and I get 2.46. 60, and that's meters squared, seconds squared, all over 2 times 9.8. I know that one. It's going to be a negative 19.6 meters per second squared. All that gives us our D. I can now take that value, minus 12.788, and that's going to give me 10.3 on top. We'll put 3, 2, and that's going to be meters squared, seconds squared, all over our negative 19.6 meters per second squared. All that equals our D, and our D is going to end up being negative point, let's just round it to 0.53 meters. It's actually 2.6, but I want to just show you with our experimental error here. So that's the distance that we calculated. That's our theoretical value between that beam and this beam. But when we measured it, it was 0.66. A lot of times students don't know how to do experimental error. So I'll actually put that formula down here for them, or if they have a sheet that they were normally going to use, but we can do it several different ways. We can do actual minus experimental. Maybe I can do it right over here. So we can say, or our theoretical versus our experimental, however you want to do it. So let's do percent error. Let's try that again. And we can end up saying the percent error is going to be the absolute value of, we'll say, our actual minus our experimental all over our actual times 100%. There's a whole bunch of different words that you can use there. They're all going to be very similar. For us, let's take that 66 as what we actually measured in experimental. We can end up saying that's what we ended up with here. Or you could say this is your experimental. Maybe we should do that. I don't know if I just said it backwards, but let's use our absolute value of 0.66 meters, because that's what I measured, minus my 0.53 meters, and I have to do my absolute value here, divided by our actual 0.66 meters times 100%. Let me put that in my calculator. So I've got my, I left my value for 0.53 in there, minus, and I'm going to plus 0.66, and then that's going to be 0.133. So let's just try that. Let me just double check, 0.66 minus my 0.53 equals 0.13. divided by my 0.66 meters cross out times 100%. Divide that by 0.66, and I get something like 0.1969. So I got to multiply that by 100%. And if I've done this correctly, that's going to be about 20% error. That is absolutely terrible. How can that be? And your students might say, wait, maybe my photo gates aren't accurate, but we've used these before and they are really, really accurate. We used our measurements of our sphere, any sphere. You can measure that using calipers or whatever you have. So at this point, you want to give your students a chance to think through where this error is coming from. So with that, I'm going to give them a few minutes before I talk anymore.